I hope you're all having a good day. We're going to talk about question 700, search in a BST. So before we go on to solving question 700, we really need to talk about what a BST is. I'm just going to write BST here. So in a binary search tree, we are given, in the first place, something called a root, since it's a tree. You can think of it as the starting point. Let's just say we have value 5 here. This is going to be our root. In a binary search tree, everything to the left of the root is going to be smaller. Let's just, for instance, we have values 3, 2, 4. Everything on, let me just use this color real quick. You can split this root into 2 halves. Everything on this left side is going to be smaller than 5. For instance, if I just triangle what the values are, 3, 2, and 4, these values are obviously going to be smaller than 5, basically. And every single value on the right side has the opposite idea, which is going to be bigger than 5. Values like 8, 7, 9. So when we are given our root, basically, I'm going to circle this in blue. Everything to the left side is going to be smaller than our root, and everything on the right side is going to be bigger than our root. So you have to have that idea in mind when you solve question, obviously 700, okay? So let's just say we have a target 2. I'm going to use 3 stars to show this is our target. And the way we want to solve this problem is by comparing the current root file with our target file until we find the target file. This might sound kind of not familiar, but it's okay. We're going to walk through this. Okay, let's look at 5. And we know our target file is 2. Let's just do a triangle. So compare 5 and 2. Is 2 bigger than 5 or smaller than 5? As I said, everything to our left side is going to be smaller. Everything on the right side is going to be bigger than 5. 2 is obviously smaller than 5. So we're going to go to the left side. We're going to go to 3. Now 3, we're looking at 3. And 3 is going to be our new root. Again, everything on the left to 3 is going to be smaller than 3. Everything that is going to be bigger than 3 is going to be on the right side of 3. We are going to look at 3 and compare it to target 2. Is 3 bigger than 2 or smaller than 2? 3 is obviously, again, smaller than 2. So we're going to go to the left side. And then we have found our target. And this is the main idea of a binary search tree. If a value is smaller, we're going to go to the left side. If a wanted value we are going to look for is bigger, we're going to go on to the right side. So having that idea in mind, we can look at example 1. We're going to, our root is going to be our 4. And as I said, I just kind of skimmed over it when I explained this, but we can move our root. Basically, we can change our root from 5 to 3, or like 5 to 8, anything you want, basically. So current root is 4, but we want to return 2. So we first want to locate 2 and return that node. So is 4 bigger than 2 or smaller than 2? 4 is obviously bigger than 2. So we're going to go to the left side and return this value, right? Return 2. In a binary search tree, we're going to go to the left side when the value is smaller and the right side when the value is bigger. Okay, This is the main idea of a BST. If you guys have any questions, please leave a comment. We are back. Before we go on, I just wanted to do one more example before we move on. So, we are given a BST and our root is 10, target 13. First thing you want to do, compare the target to our root. Is our target currently bigger than our root? Yes. Then we want to go to our right side. We changed our root from 10 to 15. This is going to be our new root. Is 13 smaller than 15 or bigger than 15? It's going to be smaller. So we go to the left side. So 13 is going to be our answer. We're going to return 13. And yeah, this is how you find the one in Node, guys. And this is going to be our answer. Okay, we are back. Let's get straight into the code. So first thing we want to do is check if our root is null. So just in case we are given a BST that's empty, we want to return null, okay? So this is going to be our first case. Now, our second case, we are going to loop through our whole binary search tree. And if we don't find our root file and we end up something in just root, right? We are going to return null because the question literally says here, if such a node does not exist, return null. So for example, if we just look at example 1 quickly, if we want to find val 4, val 4 is in the root. So let's just say we want to find like our target is 8 or val is 8. On the other hand, we're going to go to the right side. 7 is going to be our new root. But if we go right one more time, since 8 is bigger than 7, we are not able to get to that val since there's no null. So just for that case, if that case happens, we're going to return null. Second part, if our root dot val is smaller than val, we want to change our root equals root dot, what do you think? So let's just say we have val 2 right here. So, and root.val is, let's just say, bigger than our current val, our wanted val. So we want to get 2, but our current root is 2. We want to go to the left side, right? Because obviously we want to go to the left side since our val is currently smaller than our root.val. Else if, and we want to do the opposite case, just say now we have 7 and compare 7 to our root 4. 7 is obviously bigger, so we want to go to the right side. If our val is bigger than root.val, we want to go to the right. And we have one more case. If, let's put it right around here, if root.val equals val, we want to return root, basically. And yeah, that's it. Just check for indentation, any mistakes, and we are set. Let's try to run this code. Oh, sorry. So for comparing, I did it right here, but for comparing here, you obviously knew two equals. So if we run this, it's going to be correct, and it's going to be 100%. Probably. Yep, we have beaten 100%. Guys, this is the code. If you guys have any questions, please leave a comment. Thank you so much.